This video is going to be about Ito's lemma, but before we do that, I'll do a short warm-up to remind you of some of the relevant facts that you're probably already familiar with. So in the very simplest form, let's say that y equals f of x, where y and x are not just variables, but each of them is also a function of another variable. So x and y are both functions of something else, say another variable t. So in that setup, you're probably familiar with the fact that the derivative of y with respect to t, so y is a function of x, which is a function of t, you can find it by doing this. Also known as the chain rule of differential calculus. Okay, that's first simplest case. We can make it slightly more complicated by saying that what if the dependence of y is not just a straightforward dependence of y on x, but it's also separately a function of t. So you've got this function f of two variables now, t and x, where x is itself also a function of t. In that case, you have to remember how to differentiate functions of two variables. Derivative of f with respect to t, that's what this is. The f sub t here and the f sub x are the partial derivatives. Derivative of f with respect to its first variable and derivative of f with respect to its second variable. And t itself is you can consider t a function of itself if you like, with a derivative of 1, so there's like a times 1 here. But x is a function of t, and now we put dx dt in here. So that's a kind of chain rule where the intermediate is not just a single variable, but it's two variables. It's t and x. I should just note before I leave that the f sub t and the f sub x here, those are not written as fully as they might be. F sub t is supposed to really be, so it means it's still evaluated at the point tx. So we differentiate f with respect to its first variable, but after we've done that, we're still supposed to be plugging in whatever x is as the thing for the second variable. Now, Ito's lemma, the real thing. So we're going to have an Ito diffusion, I'll call it xt, and we'll write it in the way that we can now write Ito diffusions. That is, instead of just saying in words that its drift is ut and its speed is vt, we write this little formal equation to say that, roughly speaking, this is supposed to say that the increment of x is u times the increment of time plus v times a random thing which can be thought of as the increment of a Brownian motion, where the Brownian motion wt is somehow extracted out of x. Okay, so we've got that. We've got ourselves an Ito diffusion. And now we'll let y be given by this. So it's a function of xt, and perhaps it also has some separate dependence on time t. The f here, what's the f, is a function which we can differentiate twice. that it has two continuous derivatives. So f is supposed to be just an ordinary nice smooth function. In particular, people often get this wrong, so let's emphasize this. F is not random. There can't be any random variables in f. If there's anything random going on, it will have to be part of the xt, because that's the only thing here that's allowed to be random. F cannot be a stochastic integral or anything like that. Can't even be an ordinary integral. Even an ordinary non-random one it can't be, because it's got to be a function. Just a function of these two things. So in particular, notice the only way in which it depends on the process x is through the value of x at time t. It cannot depend on the value that x has at other times, at earlier times perhaps. It's just a function of two variables. That's all it can be. Then, okay, in the setup we've got here, you can maybe see what we're doing. We've had very few examples so far of Ito diffusions, but now we're going to start to get a lot more, because the conclusion of Ito's lemma will be that yt is an Ito diffusion. Actually more than that, but to begin with it says that yt is an Ito diffusion. So if you take a nice function of an Ito diffusion, you get another Ito diffusion. And more than that, we can relate the drift and speed of y to the drift and speed of x, like so. So the little formal equation that gives you the drift and speed of y will look like this. dyt is f sub t dt, f sub x dxt, so these are the partial derivatives of f with respect to its first variable and its second variable, plus is the second partial derivative of x with respect to its first variable. A term like that involves the quadratic variation. So here ft, for instance, means, as we were previously doing, although we're just writing f sub t, we mean f sub t evaluated at the point t and xt. And likewise for the other two partial derivatives involved, f sub x and f sub xx. And quadratic variation, let me just remind you about that. What's the quadratic variation of an Ito diffusion up to time t? It's the integral of its speed process. So when we write something like dqvx of t, that's an increment of this process dt. That could also be written, if we wanted a more concrete way of writing it, vt squared dt. Just a note for the future that one other way that this is sometimes written and I'll be doing this later on as well, dxt squared, which looks a bit weird, but it makes perfect sense if you remember that the definition of quadratic variation is that you add up over a lot of little subintervals in a partition the squared increments of x. So an increment of the quadratic variation is the squared increment of x. So that's Ito's lemma, written in its boldest form. And you can kind of see what's going on intuitively here. Right? We're saying that a little increment of y what would that be, given that y is a function of t and x in this way? Well, you have to multiply the partial of y with respect to t by dt, plus the increment of y that arises from changes in x, so that's f sub x times the increment of x, and then most mysteriously the second derivative has something to do with it too. It's really this second derivative term that is new here. This is not something you get when you're just dealing with ordinary functions. This is a term that arises out of the randomness involved. This only happens when things are random. And this is where the second derivative comes in. It sort of has something to do with the variance, which is why the v is coming into it. V is telling you something about the variance of increments of x. Okay, so given that we can actually write this term involving the quadratic variation like so, this dqvt thing could also be just written as vt squared dt. If we wanted to write it as lemma in a more concrete form, well, the vt squared dt, that would mean that you could combine it with this term. So there's the dt terms all combined together. Plus this other dxt term like so. Or we could go one step further, because dxt is actually given back here as ut dt plus vt dwt. So if we want to write everything completely explicitly in terms of the underlying Brownian motion, we've got ft plus ut so this is fx times a ut dt plus half bt squared. That's all the dt stuff brought together, and what's left over is that. And this is taking care of the random stuff now with a Brownian motion. So that this now completely expresses the drift and speed of y in terms of the drift and speed of x. And here's this whole term is now the drift of y. It's everything that came before the dt. And this term that remains is the speed of y. All this use of dx's and dy's seems a bit confusing or unfamiliar. It helps sometimes to remember that all we're really doing is using it as a way of writing more briefly things that could be written more formally using integrals and stochastic integrals. So the statement of Ito's lemma, for instance, here it is again, that could be written more explicitly as like so. Yt is its starting value y0 plus, and now all of these bits turn into integrals. So here's the first term, it just becomes a ds integral plus, now the second one is a stochastic integral, and the third term like that. It just takes up more space to write things in terms of all the integrals, and there's a certain nice intuition to writing things this way. You can think in terms of little increments of the processes and how they relate to each other.